Hi, Chem 151 students. Welcome back after the first exam. We're now going to start talking about Chapter 17, which is all about equilibrium. So at the very end of Chapter 16, which was about kinetics, we started to define the idea of equilibrium. So equilibrium in chemical reactions is somewhat like what you see here in this picture of an equilibrium for a physical process here. So in this container, we have some water flowing in, but there's also a spout on the side with water flowing out. And if the water is flowing in at the same rate that the water is flowing out, then the level of the water will not change. And so if you were just watching the level of the water, it would look like nothing is happening. So likewise, with chemical equilibrium, what it looks like when a reaction comes to this chemical equilibrium, it looks like it's completely stopped if we're looking at how many products and reactants are there. However, on a microscopic level, a submicroscopic level, looking at the molecules, we'd see that in fact the reaction hasn't stopped. It's just going in at the same speed in the forward direction as it is in the reverse direction. And that's how we defined equilibrium in Chapter 16. And now we're going to go more into the details of equilibrium and how we can describe equilibrium. So a very useful example of an equilibrium process that we see in the skies every day is the conversion of colorless N2O4 to NO2 brown, which has a brown color. And so this is the characteristic smog that we see in the afternoon over LA. That brown color is due to the NO2. And so here we've defined chemical equilibrium. The definition here is a little bit different than we had when we were in the kinetics chapter. We're saying it's a state that's reached when the concentrations of reactants and products remain constant over time. And this is a consequence of the fact that the forward reaction is proceeding as quickly as the reverse reaction, and therefore it appears like the concentrations of reactants and products are not changing and their amounts are not changing. It's just that they're being interconverted between each other at the same rate. And so this reaction here happens because the sunlight in the afternoon hits N2O4 in the sky, which is produced by the combustion of gasoline engines, and then that sunlight breaks this central bond between the two nitrogen atoms, and you get two NO2 molecules, which again is that smoggy brown color that we see above, LA or sometimes the Inland Empire in the afternoons. This was actually a lot worse. So if you were to look at LA, I believe this is Shanghai, but if you were to look at LA in the afternoon in the 70s or 80s, it looked like this, really brown. And that was that photochemical smog, as they call it, the NO2, which gives this brown color. In the early morning, you won't see it because the N2O4 is colorless, but in the afternoon, after the sun has shone on the N2O4 and it's been emitted in higher concentrations by vehicles on the commute to and from work, you see this brown color in the afternoon due to the NO2. So another analogy other than that water spout analogy that I had here is like two floors in a mall here, assuming that everyone's kind of flowing through the mall. You can expect that, approximately the number of people that are on one floor versus the number of people that are on the other floor will stay approximately unchanged. You'll just have, but they won't be the same people at any one time. There'll people be going up from the second floor or down from the third floor. And so equilibrium is like that. if you count the molecules, the amounts of them, products and reactants, are staying the same. However, those molecules are constantly interconverting between one another. They also call this a dynamic equilibrium, because although the amounts of everything appear to be staying the same, that does not mean that all the chemical reactions have stopped. It's just that their net product is unchanged, because the reaction is going in the reverse direction as quickly as it's going in the forward direction. So what does this look like in terms of concentration? And the answer is that it really depends on the reaction. So if we're looking at the reaction that we were discussing before, N2O4 in equilibrium with NO2, first of all, one thing you're going to notice is that what we've written here is a reaction arrow that goes in both directions, forward and backwards. And that's the way we write a reaction arrow to indicate that a reaction is at equilibrium with or can go forward and backwards quite extensively. We have a forward arrow and a backward arrow. And so we're going to see this a lot as we move forward. The next, basically until the end of the class, we're going to continue to be referring back to equilibrium. When I talked about at the beginning of the class, chemistry getting real. Chemistry gets real when we talk about what really happens in reactions, and they don't always just go forward from reactants to products. In many, many cases, if there are enough products, the reaction will go in the reverse direction. And so if we were doing an experiment like the experiment is done every day in the skies, basically, but in the morning, the cars start driving and they produce a lot of N2O4, so there's going to begin with N2O4 and not much NO2. But as the day passes, so time passes, the sun shines and some of that N2O4 is converted into NO2, so we see the concentration, this is a concentration here, of N2O4 start to decrease, and the concentration of NO2 start to increase. And you can see the concentration of NO2 rises more rapidly because every time one N2O4 reacts, we produce two NO2s. But finally, after a certain amount of time has passed, the concentrations of N2O4 and NO2 continue to remain unchanged, and so they just flatten out forever. Now, this is the situation where there was only N2O4. Let's say we had a different reaction where we had only NO2 present. And so in this reaction, the reaction would go backwards to produce some N2O4. And we can see again, as we go forward now, we're using up NO2. It is reacting together to make N2O4. So the NO2 concentration is decreasing. The N2O4 concentration is increasing. But even though we started with all NO2 here, in the end, we get the same result. The relative concentration of N2O4 over NO2 is that there is significantly more N2O4 than there is NO2 once we reach equilibrium. So in both of these experiments, at the end, the concentration of N2O4 reached 0.0337 molars, represented by this flat part here, and NO2 reached 0.0125 molars. And so the way that we can describe the way the reaction is once it's reached chemical equilibrium is to compare the amount of the products versus the reactants here, the reactants versus the products, compare how much there are to one another. Because this ratio, essentially, when expressed in a certain way that we're going to talk about, remains the same. And we're going to call that ratio, or a formulation of it, we're going to call it the equilibrium constant. It's going to tell us about how much of a reactant there will be relative to a products once equilibrium is established. What about if we look at this in terms of the rate of the reaction? So now we're not looking at concentration, we're looking at the change in concentration over time, so the molars per second here. And we have time on this axis as well. So if we're looking at the speeds of the forward reaction versus the reverse reaction, if we start with only N2O4, the reaction can only go in the forward direction. And so we will see that the reaction will go in the forward direction. As it goes in the forward direction, we'll have less and less of the reactant here, and so the forward reaction will begin to slow down. But as this reaction is going forward and time is passing here, as time is passing, this reaction is going forward and we're getting more and more of the NO2 product. So as we get higher and higher concentration of NO2, the reverse reaction begins to go faster and faster and faster. And at a certain point, the speed of the forward reaction will be the same speed as the reverse reaction. And at that point, we will have reached chemical equilibrium. Now notice, remember back in the last slide, that does not mean that we have the same amounts of products and reactants. How much product and reactant we have at equilibrium will depend on what reaction we're talking about. But for all reactions, what equilibrium means is that the rate of the forward reaction is the same as the rate of the reverse reaction. So overall, once the chemical equilibrium is reached, products like NO2 here are being made as quickly as they're being used up in the reverse reaction. So overall, it looks like the concentrations of N2O4 and NO2 are not changing. Even though they are changing, it's just you're getting the products being produced at the same rate that they're being consumed in the reverse reaction, and so there is no net change in the amount of products or reactants, even though the forward and the reverse reaction continue to go. It just means that they're going at the same speed, so the concentrations of the reactants and products are not changing. So how are we going to define this situation here? We want a way to say what are going to be the concentrations of our reactants and products once equilibrium is reached. Can we have a number that can describe what those amounts will be? And we can. This is referred to as the equilibrium constant, which is given a big K. Make sure to write a big K when you're talking about equilibrium constant, because remember, the little k represents a rate constant. So those are two different things. And we also put a subscript here, which means C for concentration. So if we're talking about a general reaction here, where the reactants are big A and big B, and the products are big C and big D, and the little letters here represent the coefficients in the balanced equation, like 1, 2, 3, 4, 5, so forth. So a, little b are those coefficients, little c and little d are those coefficients. The equilibrium constant expression will look like this. So we'll say the equilibrium constant Kc is equal to the concentrations of the products, each to the power of the coefficient in the balanced equation. Okay, so here we do use the coefficients in the balanced equation. And we're going to divide those by the concentrations of the reactants, each to the power of their coefficients in the balanced equation. And so this gives us a ratio of products versus reactants. And what this means for K is that if K is a big number, that means at equilibrium there's more products than there are reactants. So a big K is a lot of products and not a lot of reactants at equilibrium. If K is a small number for a particular reaction, this means that when you get to equilibrium, there are still a lot of reactants and there are not a lot of products. Okay, so a big K means a big top of the fraction here, a lot of products, not a lot of reactants. A small K means a lot of reactants still left at equilibrium and not many products. And overall, this expression is called the equilibrium constant expression, or it's also often called the mass action expression. Either of those are ways to describe it. So for example, if we were talking about the reaction that happens in the atmosphere above LA, the N2O4 making two NO2s, its equilibrium constant expression would have the concentration of NO2 on the top because it's the product, and we would square that because it has a 2 as the coefficient in the balanced equation. Then we would divide that by the concentration of the reactant, N2O4, and since that has a 1 in the balanced equation, that will be to the first power. And if we get this number, this can tell us something about the reaction. So notice here K is small at 25 degrees Celsius. The temperature is important here because equilibrium constants will vary with temperature. So you'll often see temperature stated with any equilibrium constant. We can see that this number is small. It's smaller than 1. And so what that means is that the bottom of this fraction is bigger than the top of this fraction. So at equilibrium, we have more N2O4 than we have NO2. And if we go back to the graph, we can see that that is in fact true. When we're at equilibrium in this reaction, whether we started with all N2O4 or we started with all NO2, either way, once we get to equilibrium, we've got more of the N2O4 reactant at equilibrium than we do the NO2 product. And so that indicates to us that our equilibrium constant should be small, because we're going to have a bigger number here on the bottom, more N2O4, and a smaller number here on the top, less NO2. So let's look at some actual data here. So this is the data that created the plot that we saw earlier. So what we saw in the plot was experiment 1 and experiment 2. So in experiment 1, they started with all N2O4 and then waited some amount of time and let the reaction come to equilibrium, and there was 0.0337 molar concentration of N2O4 and 0.0125 molar concentration of NO2. And in experiment 2, they started with all NO2 and no N2O4, and they got the same concentrations here. In experiment 3, they started with a greater amount of N2O4 than in experiment 1, but no NO2. And these were the concentrations at equilibrium. And then experiment 4, they started with a smaller amount of NO2 than they did in experiment 2, but also no N2O4, and got these concentrations. And then finally in experiment 5, they started out with some of both, and then let the reaction come to equilibrium and got these concentrations. And you'll notice here that the equilibrium constant in all these cases is the same. It doesn't matter what amounts of these things you start with. The equilibrium constant expression will give you the correct ratio of concentrations. It will always be the same. Let's and you can notice there's a little bit of difference here because in real data, we have some error on that last sig fig, but they're basically the same. So let's actually go ahead and calculate this to verify. So we do know that the equilibrium constant expression is the product NO2 on the top, and we square that because of the 2 in the balanced equation, and the bottom N2O4. And so let's plug in the values from experiment 1 and calculate what the equilibrium constant would be. Remember, when you calculate the equilibrium constant, you put in the concentrations at equilibrium, not the initial concentrations. The equilibrium constant is referring to what happens at equilibrium. So if we want to calculate an equilibrium constant, we must put in concentrations from when the reaction is at equilibrium. Okay, so now we're going to plug in some numbers here. So we're going to plug in the concentration for NO2, which is 0.0125, and we're going to square that. That's going to go on top. And then we'll put in the concentration of N2O4 from experiment 1, that's 0.0337. And let's calculate the equilibrium constant, 0.0125 squared divide by 0.0337. And we get an equilibrium constant that is 4.64 about times 10 to the minus 3. So one thing I want you to notice here is that we did not put in any units. And usually I'm really harping on you guys about units. Always keep your units. If we were to calculate the units here, it would be molars squared over molars, which would just be molar. But there is one situation in chemistry where people often leave off the units, and that is when they state the equilibrium constant. And the reason why this is that the units will vary depending on what reaction you're doing, and also what are the coefficients in the balanced equation. Basically, the units are not generally stated, or not often stated, with an equilibrium constant, because they don't really tell you anything that you didn't already know. And so if you read papers, like a lot of times they'll just put the units, but sometimes they won't. This is maybe the only situation in the physical sciences that I can think of where people leave off units, but there is a good reason for it. And so I will not require any units on your equilibrium constants or in your calculation of an equilibrium constant. That's okay for you to leave off your units for this one application, because there's a good reason why you would. Now let's calculate an equilibrium constant from our concentrations in experiment 5 now. So in this experiment, we had significant amounts of both the reactant and the product, but it doesn't make a difference, because once they come to equilibrium, we get the same equilibrium constant if we calculate it from the equilibrium concentrations. So here, the equilibrium concentration of NO2 is 0.0141 molar, and we're going to square that and put that on top of the fraction. And then on the bottom, we're going to put the concentration of N2O4, 0.0429, and now we're going to calculate the equilibrium constant. So 0.0141 squared divided by 0.0429. And of course, whenever I punch something, I hope you're punching it along with me, just to make sure you get the same answer. And we get 4.63 times 10 to the minus 3, just as it says right there. And so you can see that, yes, there's a little difference on the last sig fig, but to any scientist, because this sig fig always has a little bit of wiggle room, these two numbers are effectively the same thing. And so you can see that it doesn't matter what concentrations you start with. At the end, you're always going to get a ratio of concentrations calculated in this fashion that gives you an equilibrium constant that is constant. The only time the equilibrium constant will change is if the temperature changes. And next week, we'll talk about how the equilibrium constant is related to temperature. But that's one thing to keep in mind. So you'll see that when we're talking about equilibrium, the temperature is always mentioned, because it does matter. The equilibrium constant will be the same as long as we're at the same temperature. So, as we mentioned in chapter 16, the last chapter, there is a link between chemical kinetics and chemical equilibrium, and that has to do with the forward and reverse rates of reaction. So for this general reaction that we see here, notice we've left off the coefficients. Why is this? This is because we want to emphasize that when you're writing rate laws for reactions that aren't elementary steps, you should not be writing in the coefficients as exponents in the equation. So there is a little bit of a breakdown in this analogy. It does work out because if you sum all the reverse and forward elementary steps, things cancel just the right way, but we don't have to go really into that level of detail. We can say, the forward reaction is going to be some rate constant times concentration of A to some power, concentration of B to some power. We're going to leave those off. And the rate of the reverse reaction is a rate constant for the reverse reaction times concentration of the product, concentration of the other product, because these are in fact the reactants of the reverse reaction. And so that's the way we wrote rate laws, if we're just not considering the exponents, just for the simplicity of making the analogy. So at equilibrium, here, we said that the rate of the forward reaction equals the rate of the reverse reaction. That's how the other way that we define equilibrium. And so if we put our pseudo rate law here for the forward reaction and make that equal to the pseudo rate law we have here for the reverse reaction, then we can divide both sides by the KF side here. And we get some ratio of rate constants times the concentration of the products over the concentration of the reactants. And so this is a very loose type of association, but I wanted you to kind of see, and they do present it in your book, that there is some type of relationship. This is glossing over a lot of details, but so here we can see that what is essentially happening is that this ratio of concentrations is proportional to our ratio of our rate constants. So if the forward reaction is faster than the reverse reaction, it has a bigger rate constant, then we're going to have more products. So we expect to have, because it's going to be making more products faster than it's making reactants, so we're going to expect a bigger K. If the reverse reaction here has a bigger rate constant, that means the reverse reaction is in general going faster than the forward reaction. So we would expect a small equilibrium constant, a lot of reactants at equilibrium, not a lot of products. That's really all I'm going to say about that relationship between equilibrium and kinetics. When we move forward into the thermodynamics chapter near the end of the class, we'll have very, very strong links between the equilibrium constant and other important thermodynamic data for a particular reaction, and that link will be very strong. This is a very weak link to kind of get the idea across that basically a fast forward reaction is going to result in a lot of products, so you're going to have big K. Fast reverse reaction is going to mean you're not going to have a lot of products, you're going to have a lot of reactants, so it will correspond to a smaller K. But there's not a strong numerical link here that's easy to talk about. It's just kind of a loose connection between the two. So how are we going to use our equilibrium constant? Here's an example question where we could calculate an equilibrium constant, and then later in the third lecture I give you this week, we'll talk about how we can actually use the equilibrium constant to calculate equilibrium concentrations, and we'll go into much depth on that next week. But let's say we've got these equilibrium concentrations for this reaction. So this is the decomposition of ammonia to nitrogen gas and hydrogen gas. At equilibrium, we have a concentration of 0.0225 molar for ammonia, 0.114 molar for nitrogen, and 0.324 molar for hydrogen. And the question tells us that we should calculate the K. So first, you'll want to write the expression for K. So Kc here is going to be the product concentrations to their power in the balanced equation. So we'll have the concentration of nitrogen, and we're going to put that to the first power, so we don't have to write a 1 there. And then we're going to multiply that. Make sure you're multiplying here. We're multiplying times the concentration of hydrogen. We're cubing that, and we're going to divide here by the reactant, the concentration of ammonia, and we're going to square that. So now let's plug these amounts in, and notice these have to be equilibrium concentrations, right? Otherwise this does not apply. So we're going to plug in the nitrogen concentration, 0.114, and again, only with equilibrium constants it's okay to leave your units off. We're going to leave off molar, and then we're going to put the concentration of the hydrogen, 0.342, and we're going to put that to the third power. And then we're going to divide by our concentration of ammonia, 0.0225, and that we're going to square. Okay, so let's plug this into our calculator. 0.114 times 0.342 to the third power, and then divide by 0.0225 squared, and that's going to equal about 9. 9 point to 3 sig figs, 9.01. And again, we don't have to put units here for a equilibrium constant. Let me make sure okay, yeah. And so that's the problem is done there. We have gotten a rate constant. Let me just make sure that I punch the calculator right. Yes, this looks good. Okay. All right. And so that's how you would calculate an equilibrium constant if given the equilibrium concentrations. So again, this here is called the equilibrium constant or mass action expression. So if the textbook or I ask you to write the equilibrium constant or mass action expression, we're asking for this. If you plug in equilibrium concentrations to the equilibrium constant expression, you can get the equilibrium constant. Okay, and that's going to conclude the first lecture about the equilibrium constant. As we move forward in the next lecture, we're going to talk about the reaction quotient, which is called Q. So I'll see you in the next one.